People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
This episode is all about the chain rule and how it relates to a simple mathematical problem about walking a dog. And one of the topics we cover has to do with energy. To that end, our partner, Brilliant.org, has a series of courses called The Road to Calculus, which will give you a robust start in understanding calculus. I love how the course starts with pre-calculus and takes you all the way through subjects like trigonometry and integral calculus, and even simple motion problems similar to the ones here. To support your education in math and physics, go to www.brilliant.org/breakingmath and sign up for free. The first 200 Breaking Math listeners can save 20% off the annual subscription, which we've been using. And now, back to the episode.
This is Sophia.
And this is Gabriel.
And you're listening to Problem Episode 2, Walk the Dog. And as you noticed, this week we're doing another problem episode.
These are fun. These are something that we don't do too often, but we're going to do much more often. And we're going to start doing them after other episodes. So our last episode was one on the Ben Orlin book called Change is the Only Constant, which is a book about calculus. So we're going to do a problem episode all about calculus.
But first, let's get some plugs out of the way. You can support us on Patreon at patreon.com/breakingmath. You can get the Tensor poster for $22.46 monthly donation there. The Tensor poster is a poster that teaches some of the fundamentals behind tensors, which are objects used in Einstein's general theory of relativity. They're basically like multidimensional matrices or vectors.
This poster is a perfect gift for any fans of astrophysics or Einstein's mathematics or anything like that. They will love it.
Or even Riemann, because it has Riemannian geometry in the Riemann tensor.
That's right.
And if you don't feel like buying that for a monthly recurring donation, hold on. We also have $5 a month. You can get outlines of the show and ad-list versions of the show. And for $1, we'll give you a shout out. People have given us money before, but no one's wanted a shout out so far. So you could be the first.
That's right. You could be the first one. That'd be quite interesting. What kind of creative names would people send in?
Creative names?
Seymour, Butts, I don't know.
Oh yeah, that's right. I forgot to mention that the way that the shout outs work on the podcast is that we give you like you say, like your name is like your name is Seymour and your favorite math thing is like numbers. I don't know. So it'll be like, we have a fan named Riemann. Crap. We have a fan named God, I cannot remember the name I just said.
Seymour.
God. We have a friend named, whatever. You understand it by this time.
Yeah.
Anyway, you could also buy our poster outright on Facebook for $22.46 plus $12.50 shipping and handling at facebook.com/breakingmathpodcast, at twitter.com/breakingmathpod, twitter.com/breakingmathpod, and you can just check our website out, including some cool applets and stuff like that at breakingmathpodcast.com.
So, as we had mentioned earlier, this particular episode is a problems episode. Now, I'm pretty excited. Sophia had told me that she had cooked up this episode herself, and I was quite excited to see what she came up with. All that I knew is that it involved calculus. So, Sophia, do you want to tell us a little bit about what you cooked up for everyone?
What I cooked up was the proof that Ben Orland does not have a monopoly on calculus. He would have you believe so. No, but no, he's a great friend of the podcast, and it's basically a problem about walking your dog. So it's like, I mean, if we want to just dive right into it, and then we'll do a sound.
Oh, and also, I was going to add one more thing. Just
Okay.
We've actually had some requests from listeners of the show, including teachers, who have asked us specifically to work through certain problems. Now, I love mathematics and I love understanding things, so I think that is a perfectly justifiable request, and this is our second attempt to do so. So, of course, the theme is calculus. We will explain to you all the problem, the setup. We will then explain the execution of how you solve it. Now, of course, we'll be talking, so it should be very listener-friendly, and it should be very, very clear.
All right, so here's the problem. Suppose you're walking your dog around a park, and the park has like a sidewalk on the outside part of it. Now suppose there's a corner in the sidewalk coming up that has a right angle in it, and has two long, straight, like segments of sidewalk leading up to the angle, like the corner of a square. So does that make sense so far?
Following so far.
All right, cool. So if you're pulled along by your dog, so your speed depends on your dog's speed, and your dog chooses to move at a constant speed after turning the corner, and if your leash has a constant length, how do you determine how fast you are moving when the dog is a certain distance away from the corner?
Okay, so you say, just to recap these, first of all, you've got a very, very well-behaved dog. That is, the dog is going at a constant rate and not accelerating, as my dog does.
Yep, to make this problem workable.
Now, the other things to consider are, you've got the lines, you've got a right angle turn, you also have a constant length of a leash, any length at all, but it's a constant, it's a fixed length.
I really just realized something. For reasons we'll explain later, the dog does not have to be moving at a constant speed. It just has to be determining your speed.
Oh, okay.
Because what we're going to figure out, a spoiler alert, is how fast we are moving relative to the dog. So based on our position, so if we know how fast the dog is moving at that point, then we will know how fast we are moving if we can figure out everything else.
Okay, very good.
But yeah, cool. Does everything else make sense too?
I think so. Yeah, so far so good.
Do you want to sum up the problem?
Sure, absolutely. So the ladder, as Sophie had explained, the ladder is the exact same thing as this problem with walking a dog around a corner. Now the right angle would be the path down the building, and then the right angle is at the ground, where the ground goes horizontal. As a ladder is falling, you've got the two legs that touch that wall, and they are traveling down that wall. You also have two legs on the ground that are traveling away from the wall.
Yep.
Right? Okay, and then as you had said, there is a change in speed.
Yeah, and so let's say you start lowering the top of the ladder down. Like let's say you put some wheels on the bottom of the ladder, and you start lowering the ladder down the wall with a rope. Mm-hmm. If you start at the very top, if you lower it down like a foot, the bottom is going to move pretty much about a foot, right?
Yes.
But if the ladder is almost horizontal with the ground and you move it a foot down, it's not going to move a foot horizontally.
Mm-hmm.
So that is the calculus in the problem.
Now, for this next part of the podcast, we are going to do the setup. That is, we're going to set up how we're going to solve this problem. We know that there is a triangle with a corner being the corner in the sidewalk, and the 2 points connected by the hypotenuse being the position of you and your dog with the leash.
Yeah, so let's say that this is like a triangle. I mean, let's say that like the dog is like 3 meters away from the corner, right? Mm-hmm. And you're 4 meters away from the corner. That would mean that you had a 5 meter long leash, right?
Yes.
Because 3 squared plus 4 squared equals 5 squared?
Yes.
So that is one thing that we have to notice, which we could we're going to call that D person and D dog for distance of person and distance of dog. Or actually, we should just say distance because D will get that confused for the derivative D.
Okay, sure, sure. So we use the term distance. And as you said earlier, you can start with the Pythagorean theorem, which gives you the length of the leash, as well as the distance from you to the corner and the dog to the corner.
Yeah, so the distance from you to the corner squared plus the distance from the dog to the corner squared is equal to the length of the leash squared. And we're of course assuming that the leash stays completely taut. So basically, the dog is pulling you along as much as you can go, basically.
Yes, and in the example of the ladder, when you've got a ladder placed across, that's leaning up on a building, the length of the ladder is the hypotenuse. So that's obviously a constant length as well.
Yeah, and we know that we have the velocity of the dog because it's moving at a constant speed, right?
Mm-hmm. Correct.
And so we know that's d distance of dog over dt, which is the derivative of the dog with respect to time, because the dog is moving at a constant speed. So we could also, that's basically saying that the velocity of the dog, we could say that velocity of dog is equal to the derivative of the dog with respect to time.
Mm-hmm.
Or the derivative of the distance between the dog to the corner with respect to time.
We are solving for the derivative of the distance of the person, or you, to the corner with respect to time. Okay.
So since we have the formula with the two unknowns being the distance between the person in the corner and the distance between the dog in the corner, we can find the derivative of our distance, the distance between the person in the corner, with respect to the distance between the dog in the corner.
Mm-hmm. This is useful because we have the derivative of the distance from the dog with respect to time already, and we can use the chain rule.
Yeah, of course. Yeah, since we already have the velocity. Yeah, and the chain rule basically states it allows you to take two derivatives and create a new derivative with it. It's kind of like multiplying fractions, but with derivatives. So it basically states that how fast some quantity A changes with respect to some quantity C is as fast as A changes with respect to some other variable or differentiator, B, times how fast B changes with respect to C.
Now, with respect to the ladder, if it's being lowered, and I do differentiate being lowered with a rope as opposed to being dropped in free fall, in which case it would be accelerating, the ladder falling is not accelerating, it's being lowered at a constant speed, but let's just say we don't know the speed. The two variables would be how fast the top of the ladder is going toward the ground, and how fast the legs of the ladder, where they touch the ground, how fast they're moving horizontally across the ground.
Well, almost. The two variables in this case would be the height, the distance between the floor and the top of the ladder, and the distance between the wall and the bottom of the ladder.
Okay, fair enough.
And then we could see how and it is an important distinction because if we know how fast if we know that, then we could say, then we can determine the distance between the wall and the bottom of the ladder in terms of the distance between the top of the ladder and the floor, which means that we could see how much the distance between the floor and the top changes when the distance between the floor and the bottom changes. So if it moves by like 1 meter on the bottom, or how much does the top move? And how about half a meter? How much does the top move? How about a quarter meter? And so on until we have the limit that represents a derivative.
Now, before we go further, I think for an intuitive approach, I'm going to use a similar example. Suppose you had a bunch of stores with prices changing gradually from one area to another and all over time. If you were to walk a certain path, you could go to the stores and get the average price of, say, bread. You can notice that the faster you move, the faster the average price will change because you are moving from one area to another more quickly. This means that for you, the derivative of price with respect to time is equal to the derivative of price with respect to location times the derivative of location with respect to time.
Yeah, so it is also like if you listen to the episode, it's like the needle scratch problem. It's if you have two derivatives, you really can relate them like that. The intuition for this problem specifically is that if your dog goes twice as fast, right, then you're going to be going around the curve twice as fast at that point that you are at, right?
Yes.
So like if your dog goes twice as fast, then the problem just speeds up by twice.
Mm-hmm. Correct.
Therefore, if you know how fast your dog is going, and you know how much and you know like your position with respect to your dog's position, then you know that, and you know how much your position changes with respect to your dog's position changing, then you can figure out how fast you were moving at a certain point in time when your dog was moving at a certain speed at a certain place.
Now we'll go ahead and move on to the actual solution of this problem with plugging in variables and cranking out the mathematics. To recap, we know that the distance between the person and the corner squared plus the distance between the dog and the corner squared, and again the dog is on the other side of the corner while the person is before the corner, equals the distance of the leash squared. That is the Pythagorean theorem. We also know that the distance of the person equals the square root of the length of the leash squared minus the distance between the dog and the corner squared. That's also the Pythagorean theorem, just rearranged.
Yeah, and so now since we have d person, or distance of the person with respect to the corner, from now on we're just going to not say with respect to the corner, we'll just say just distance of the person. So we know since we know the distance of the person with respect to the distance of the dog, we could figure out d distance of person over d distance of dog, which turns out, and we're not going to go over this part because this is just a bunch of plugging in. You could do this on Wolfram Alpha. This episode is mostly about concepts. It's negative distance of dog over square root of leash length squared minus distance of dog squared. And if you'll notice, this is actually negative distance of dog over distance of person.
Yep. Now we apply the chain rule, and we see that the derivative of the distance of the person with respect to time is equal to the derivative of the distance of the person with respect to the derivative of the distance of the dog times the derivative of the distance of the dog with respect to time.
And of course, because derivative of the distance of something with respect to time is equal to the velocity of that thing, you can also say that this is the velocity of the person is equal to the derivative of the distance of the person with respect to the distance of the dog times the velocity of the dog. So as you'll notice, when the dog just starts out, you don't move at all, because it's velocity of dog times distance of dog over distance of person, right? Once it's all hashed out,
yes,
that's how it works out. So let's say your dog is moving 3 meters per second, and it's 3 meters away from the corner, and you're 4 meters away from the corner. Then it is is moving at 3/4 of the speed. You're moving at 3/4 the speed of your dog, and you could just keep plugging in numbers like that. But it's seriously just that easy. The negative velocity of your dog times the ratio of the dog's distance to the corner to your distance to the corner is how fast you're moving.
Now to illustrate this problem, you could actually do a side-by-side comparison using a plot of the rate of the dog and the rate of the person, or of yourself, and you'd notice that they are not the same at any given point. Well, they might be at one point, but
yeah. If you have in front of you a laptop and a phone, get your phone and lean it up against your laptop screen and put your laptop screen up at a right angle. Now notice that when you slide the bottom of your phone a little bit when it's resting right against the screen, the top doesn't move almost anything. Now put it at like a 45-degree angle resting between your keyboard and the screen. Now you'll move the bottom the same amount and the top will move a lot more. And that's the intuition behind this problem. And if you think about a thing sliding down a wall, it goes slow, 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 fast.
Mm-hmm.
Yeah.
What really surprised me was when I first heard this problem without actually examining it further, I assumed that the two rates of change would be the exact same, but they most certainly are not.
Yeah, it's interesting, right? And I mean, some of the assumptions that we made, I think, don't even apply for other shapes. You know, like for example, if there was a weird like squiggly shape and we were being led on by our dog, led by our dog, there wouldn't even be a guarantee of us of the leash staying the same length, for example. because then the dog moving as fast as they could wouldn't necessarily keep it taut, like if the path looped back, for example.
Mhm.
So I hope you all enjoyed this problem episode of Breaking Math, and be sure to. Well, I was going to tell you where you can listen to the podcast, but you're listening to it.
Yep, exactly. Be sure to send us an email if there's a problem that you would like us to explore in great detail on this show. There's so many out there that we would love listener input.
That's a wrap. Oh, wait, email for listener input. breakingmathpodcast@gmail.com.
That's right. And that's it. With that, you have your problem solved, and you can figure out the velocity of you and your dog.
Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencastr. Zencastr is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencastr has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencastr paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your